Hello all. Today we will see another topic from database design, that is properties of relational decompositions. So today's outline will give an introduction, then we'll talk about dependency preservation, lossless join, and algorithm to test lossless join property, and we'll discuss about binary decomposition, and there also this lossless join property. So, as an introduction, we have seen several examples of this decomposition earlier. So, for decomposition, let's consider a universal relation schema. So, what is a universal relation schema? It is a relation schema R with the set of attributes A1 to AN that includes all the attributes of the database. Okay, so we have n attributes here. So when this relation schema contains all these n attributes, it is a universal relation schema. Okay, so decomposition is the process of decomposing the universal relation schema R into a set of relation schemas, and you can call that set as D, that contains R1 to Rm. Okay, and that will become the relational database schema by using the functional dependencies. Okay, so we are decomposing this universal relation schema R into a set of relation schemas R1 to Rm, another set. Okay, and that will become the relational database schema by using the functional dependencies. And here we can, when we decompose this relations, we can talk about this kind of properties of this relational decompositions. Okay, we have seen these properties earlier. We'll have a detailed look here. The first property is that it is attribute preservation condition. Okay, so even when you perform this decomposition, attribute preservation condition should be satisfied. Okay, that is, we consider a relation schema where there are n attributes a1 to an. So even though you perform decomposition, all of these n attributes should appear in some of the relations. Okay, so after decomposition, you will get some m relation schemas. So you have n attributes. All of these n attributes should appear in some of the relation schemas. Okay, that is known as this attribute preservation um, condition. That is, each attribute in R will appear in at least one relation schema Ri in the decomposition, so that no attributes are lost. Okay, so which means all the attributes should be there in some of the relation schemas, and which means you should not lose any of the attributes. Okay, and each individual relation Ri in the decomposition D should be BCNF or 3NF. Okay, so this resultant relation schema should be normalized. Okay, or that is in BCNF or at least in 3NF. Okay, and it should prevent from generating spurious tuples. Okay, so even though you decompose this into um, some number of relation schema, it should not generate spurious tuples. We discussed about spurious tuples earlier. So this decomposition should prevent generation of this spurious tuples, that is actually the unwanted data or wrong data in the database. Okay, and Last condition is that, or last property is dependency preservation. That is, we discussed about this relation schema with some functional dependencies. Okay, whenever even though you decompose this relation schema into some number of relations, all the functional dependencies should be preserved. Okay, so these are the properties of relational decompositions. So we'll first see this relational, um, the result of this spurious tuples. This example we have already seen, that is employee locations, employee underscore project one. So here you have E name and P location, and employee underscore project one is SSN. This is after decomposition. Okay. And a P number as P name and P location. So when you perform a natural join on this two relations, employee underscore project one and employee underscore locations. Um, for just for suppose you consider SSN equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are two relations, that is employee underscore project one and employee underscore locations. So here the common attribute is P location, and it will return all the tuples which satisfy this which satisfies the condition that if P locations are same, corresponding tuples will be written. So, uh, based on that, the result will be you will get 1, 2, 3, 4, SSN 1, 2, 3, 4, 5, 6, 7, 8, 9. P number 1 as 32.5, P name product X, Bell array, and Smith, comma John B. And the next tuple is 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, that is SSN, and we know SSN is a primary key that will uniquely identify an employee. But here, this same SSN 1, 2, 3, 4, 5, 6, 7, 8, 9 is for Smith, John B, and for English, Joyce A. Okay, so that is actually a wrong data in the database, or I can call it as a spurious tuple. Okay. So before going into this dependency preservation, so we'll have some um, definitions. Okay, the first definition that we are going to see is projection, and projection means we can define it like this. We have given a set of functional dependencies F on R, where R is the universal relation schema. So we have a set of dependencies F, and the projection of F on R, we can denote it by pi of Ri, pi Ri of F. Okay, that is projection of this F on Ri. And here Ri is a subset of R. What is Ri? Ri is a subset of R. That is that we get after decomposition of this R. And this projection is the set of dependencies x to y in F closure. Okay. So this projection of F on R means that is again another set of dependencies x to y in F closure. What is F closure? F closure is closure of this set of functional dependencies. Okay. So here the condition is that here again we are taking this dependencies like x to y, but it should satisfy some condition such that the attributes in x union y are all contained in Ri. So here, even though you take a function dependency which is in F plus, you will return that as the projection of F on Ri. But the condition is, we know that for this function dependency, the left hand side and right hand side are actually sets of attributes. So when you take their union, x union y, all these attributes are contained in the relation Ri, which we are talking about. Okay. So if this function dependency has left hand side x, right hand side y, and this the attributes corresponding to x and corresponding to y are in Ri, then you can return as the projection of f on Ri. And you can take all such dependencies from this f plus. Okay, and that set is pi Ri of f. Okay, so dependency preservation property of a decomposition. So what is this dependency preservation property of a decomposition? So a decomposition D is equal to the set R1 to Rn, okay, of this capital R is dependency preserving with respect to F. Okay, so we have a functional dependency set that is F. So we are saying that a decomposition D is equal to R1 to Rm of this capital R is dependency preserving with respect to F if the union of the projections of F on each Ri in capital D is equivalent to F. Okay. So you have R1 to Rm relations. Now you take projections of F on each of this Ri and take their union. So what you are expected here? You are expected to get f cross f again, okay, because you should generate or you should preserve all the dependencies in the original relation or the universal relation. So when you take the union of the projections of f on each Ri in D is equivalent to f, you will get the original set of functional dependencies if you take union of projections of f. And when you take their closure, that is equivalent to F closure. Okay, so pi R1 of F union pi R2 of F union etc. union pi Rm of F and closure of that. That will give you F closure. Okay. Now let's see one example where the dependency is preserved. And this example we have seen already. That is loads 1 and we have loads 2. Loads 1 has property ID number, county name, load number, area and price. And we have three functional dependencies here. And we have loads 2 that is with county name and tax rate, that is FT3. And we know that this actually is in 3NF. Okay. But when you see this loads 1, you have this function dependencies. Property ID determines the county name, load number, area, price. That is okay. Then again, county name determines property number, or load number determines this property ID number, and load number determines the area, price, etc. Okay. So there you have FD4 also. When you have FD4, that says what area determines this price. Okay, so that when you consider this kind of relation, you can say that this is in 2NF, that satisfies the conditions of 2NF, but this is not in 3NF because the last dependency FT4, that is between area and price, where this area is not the super key or price is not a prime attribute. Okay, this is not in what do you say, in 3NF. So you can decompose this loads 1 alone into loads 1A and loads 1B. This we have done already. Uh, what are the attributes corresponding to loads 1A? There is property ID number, then county name, load number, area. That is one relation, loads 1A. And you have loads 1B. There also you have area and price. So area is now a primary key, and area to price will be in 3NF, and already these are in 3NF. Okay, either when you have x to y, either x is super key or Y is a prime attribute. Okay, so all the conditions are satisfied. Now this is in 3NF and it preserves all the dependencies in the original relation. Okay, so this is a dependency preservation example. And you can see a non-dependency preserving example also. So consider again the same relation loads 1A, that is loads 1A, that is with um, two function dependencies. And suppose we have one more dependency, that is FD5, that is between AD and county name. Okay, AD and county name. Suppose that kind of a function dependency is there. This is obviously in uh, 3NF because even though you have area to county name is, as we have seen, county name is a prime attribute. So that condition is true. But this is not in BCNF. BCNF says that X should be a super key. Okay, so here area is not a super key. So this is not in BCNF. So what we can do is again decompose into loads 1AX and loads 1AY. And this first relation will have property ID number, AD and the load number, and second relation will have AD and county name. Okay, so we are decomposing this in such a way that this condition or this dependency appears there. Okay, that is FD5. So here what happens is you have area as the primary key. So area to county name is the function dependency, which is in BCNF. And consider here you have some function dependencies like um, FD1 is there. There it determines property ID number, then area, load number. That is okay. But you have a county name that determines property ID number and county name determines the lot number, county name determines area. Okay, so this FD2 is lost when you decompose this loads 1A into loads 1AX and loads 1A. Okay, so this is a non-dependency preserving example. You cannot, after decomposition, you lost one dependency from the original relation. Okay. So this is another example. So non-dependency preserving. We have a relation teach. There you have student, then course, instructor, and we have some functional dependencies like student course to instructor and instructor to course. Okay, these are the two functional dependencies. So you can decompose this teach relation in three ways. We have seen this earlier. Anyway, R1, we have the first decomposition is like we have R1 and R2, R1 with attributes student comma instructor and R2 with student comma course. Okay, and we have R1 second decomposition, that is R1 with course comma instructor, then course comma student. Then R1 instructor comma course and R2 is instructor comma student. Okay. So these are three possible decompositions for this. But the problem with this kind of a decomposition is that we cannot or we lost one functional dependency, that is FT1 student comma course determines this instructor. Okay, because each of this relation has only two attributes, so this cannot be uh, true. That is a student comma course determines instructor. That cannot be there in any of the decompositions. Okay, so this is a non-dependency preserving example. And even though this is the case, what we can claim is that is a dependency preservation property of a decomposition. There we can make one claim. It is always possible to find a dependency preserving decomposition D with respect to F such that each relation Ri in D is in 3NF. Okay, so you can make sure that you will be able to decompose relation R into D without or when this each of this Ri in D will be in 3NF, okay, or without altering this 3NF, okay. You can make sure that you will get relations which satisfies or which is in 3NF. But when you go for BCNF, uh, most of the cases you cannot preserve dependency in the relations. Okay, so one claim you can make is that it is always possible. Okay, which means it is always possible to find a dependency preserving decomposition D with respect to F such that each relation Ri is in. So you can guarantee that your relation will be in 3NF even though you perform this decomposition and but we cannot guarantee the dependency preservation property in BCNF. Okay, so for converting or to make this relation in BCNF, we need to perform some decomposition. So that time you cannot guarantee that the dependency preservation property will be there. Okay, but it is always possible to find a dependency preserving decomposition which is in 3NF. Next is a non-additive or lossless joint property of a decomposition. Okay, non-additive or lossless joint property of a decomposition. So let's see what is meant by this non-additive lossless joint property. So the definition is a decomposition D is equal to the set R1 to Rm of capital R has the lossless, that is non-additive joint property with respect to the set of dependencies F on R if for every relation state R of capital R that satisfies this capital F, the following holds. Okay, suppose you have a decomposition for this capital R like D is equal to R1 to Rm. Okay, and this has the lossless or non-additive joint property with respect to the set of dependencies F on R if every relation state R of capital R satisfies F, then the following holds. So here where star is a natural join of all the relations in D, and you can say star of pi R1 of R, pi R2 of R, comma, etc., comma, pi rm of R, that will give you R itself. Okay, so here what we say is that when we have so many M relations, R1 to Rm relations, and when you take every relation state R, and suppose you take pi R1 of R, okay, then take the um, natural join. So when you perform this natural join, you get this R again. Okay, so which means whatever data were there in R, that is um, that will be preserved when you perform this R1 to Rm. Okay, decomposition like R1 to R. Whatever data was there, that is not going, you are not going to lose any of them, that will be there in R1 to R. That is why when you perform this natural join, you get this kind of R itself. Okay, so you get relation state of the original relation. Okay, when you perform the natural join on all of this, and nothing more will be added to this data. Okay, whatever data were there, you'll get that. Nothing more will be added. That's why it is known as a non-additive or lossless, you are not going to lose anything and you are not going to add anything to the data. Okay, so that is a lossless join property. This is how you can state that you have a decomposition and you have relation state R. Then when you perform natural join on the projections, you will get the same relation state R. And you can test this lossless join property, and there is an algorithm for testing this lossless join property. So that is, when you perform a decomposition, you can check whether the lossless join property is preserved or not. Okay, so a universal relation, so input to this algorithm is a universal relation R, a decomposition D that is equal to R1 to Rm of capital R, and a set F of functional dependencies. Okay. The step is like this. Create an initial matrix S with one row I for each relation Ri in D and one column J for each attribute Aj in capital R. So you are trying to create a matrix corresponding to these relations and attributes. So rows of this matrix S will be relations. Okay, so suppose you have m relations, then m rows will be there, and columns means their attributes. So if you have n attributes, then n columns will be there. Okay, so that is a matrix, and you can set values to this matrix, that is set S of I comma j, that is ith row and jth column. That value you can set initially as Bij for all matrix entries. For all matrix entries, S of I comma j will be set as Bij, where Bij, each Bij is a distinct symbol associated with the indices I comma j. And for each row I representing a relation schema Ri, for each column J representing attribute Aj, if the relation Ri includes attribute Aj, then set S of I comma j as Aj. Okay, suppose you have a relation Ri and you are talking about jth attribute. Suppose this Ri includes this attribute, jth attribute, then you can reassign S of I comma j as Aj. But again, Aj is a distinct symbol associated with that. So we are starting with the Bij, and if particular relation has a particular attribute, then that corresponding entry will be set as Aj, where j is the column number. And you will repeat the following loop until a complete loop execution results in no changes to S. So here you take each functional dependency x to y in capital F. Okay. And for all rows in S that have the same symbols in the columns corresponding to attributes in X. Suppose you take this X, and again we know X is a set of attributes. So take all the columns for all rows in X that have the same symbols in the columns corresponding to. So corresponding to this particular row, you take the columns corresponding to attributes in X. Okay, suppose all these columns have the same values corresponding to this attribute, then what we can do? Okay, so if they have the same values, then if any of the rows has a symbol A for the column, set the other rows to that same A symbol. If you have A in that particular column, then any of these columns have A in that A symbol for that column, then set other rows to that same symbol. Okay, if no A symbol is there, then you take one of the B's and assign that to all the. What you are trying to do is you are trying to make all the column values the same corresponding to this attributes in the function dependency. Okay, and finally, if a row is made up of entirely A symbols, then the decomposition, you can assume that it has a non-additive join property. Otherwise, it does not. So we'll see an example that time it it will be clear to me. So again the relation universal relation is SSN, E name, P number, P name, P location and hours. So you are decomposing that into two relations R1 and R2, where it is employee underscore locations E, and that has attributes E name comma P location, and you have R2, that is employee underscore project one, with attributes SSN comma P number comma hours comma P name comma P location, and with uh, the set of functional dependencies F, that is SSN to E name, P number to P name comma P location, SSN comma P number to hours. Okay, so according to the algorithm, first step is to create a matrix, yes, and number of rows will be equivalent to number of relations, and number of columns means number of attributes. So you have two relations here, so you have R1 and R2, two rows, and how many attributes? You have six attributes here, so six columns. Okay, so that is the first step. Second step is to populate this matrix. That is by the initial value will be S of I comma equal to Bij for all matrix entries. So you have R1. R1 will have, this is first column. So B11, it is B12, B13, B14, B15, B16. Then R2 is B21, B22, B23, B24, B25 and B26. So that is the first step. And second step is that for each row I representing relation schema Ri, and for each column j representing attribute aj, if the relation Ri includes attribute aj, then set S of I comma j as aj. So you take each relation R1. So take first row. R1 has E name and P location. So what will happen? E name is here, that is a second attribute. So this is overwritten as A2. Okay, B12 is gone and you have A2 here. And the second attribute is P location. P location is the fifth attribute. So corresponding to R1, you have an A5 here. Okay, and for R2, that is you have five attributes: SSN, P number, hours, P name, P location. So you can assign SSN as the first column, that is A1. So E name is not there. P number, so that is A3. Hours, that is A6. Then P name is A4. P location is A5. Now you have this kind of A5. Okay, all this entries. Next step is you take each functional dependency and check. Suppose the functional dependency is x to y. Then for all rows in S that have the same symbols in the columns corresponding to attributes in X. Same symbols in the columns corresponding to attributes in X. And if that same symbol is, you take the other part, Y's column. Okay. So you have X, X has the same value, then check Y part. Okay. There, if you have an A, then copy that A to all other columns or all other rows corresponding to this particular column. Or if no A is there, then choose one. So here you have SSN to E name. There X is SSN. So take SSN corresponding to the relations. So here S has B11 and next value is A1. So no rows has the same symbol for column corresponding to this SSN. Okay, that is the first step. So we should find out all rows in S that have the same symbols in the columns corresponding to the attributes in X. So corresponding to this, they are distinct symbols. So you don't need to make any changes. Okay, and consider the next functional dependency, that is P number to P name, comma P location. So take P number. P number values are B13 and A3. Again, they are distinct values. So there is no need to make any adjustment. Then SSN comma P number to ours. So take the combo SSN comma P number. SSN and P number. B11, B13, A1, A3. So both are different. So no adjustment is required. And the last step says If a row is made up entirely of A symbols, then it has the non-additive join property. So here R1 is B11, A2, B13, B14, A5, B16, and R2 is A1, B22, A3, A4, A5, A6. So here no row has all A's. So even it means that this decomposition is not preserving this non-additive join property. Okay, it does not preserve this non-additive join property. So let's see one example. It preserves this non-additive join property. So you have employee, project, and work zone. Three relations. So after you have this original relation R, universal relation, and you decompose that into employee, project, and work zone. So D is equal to R1, R2, R3. The set R1, R2, R3. So R is the same, and R1 with attributes SSN, comma E name, R2 with attributes P number, P name locations, R3 SSN, P number, Rs. And you have the same functional dependencies, that is SSN to E name, P number to P name, comma P location, SSN, comma P number to Rs. Okay, so the first step is to create this matrix. So matrix is R1, R2, R3, SSN, E name, P number, P name, P location, and Rs. So you have entries B11, B12, B13, B14, etc. So you can fill all the entries. And next step is you take each relation and override these values. R1 has SSN, comma E name. So SSN and E name. There you can change the values. So you get corresponding to SSN, you have A1. Corresponding to E name, you have A2. Okay. And for R2, P number, P name, P location. So there A3, A4, A5. And works on SSN, P number, and Rs, A6. Okay. That is the third relation. So you have set all these values. Now you have a loop in this algorithm that takes each functional dependency x to y, and for all rows in S that have the same symbols in the columns corresponding to. So you take attributes in X and you check the rows with if this X has the same values. If they have the same values, then look at Y part. If Y has A, then copy that everywhere. Okay. So that is the algorithm. So here, take the first functional dependency, that is SSN to E name. So you have SSN here, B12 and A1. So value of this SSN is repeated here. Okay. So A1 you have here and A1 here also. So these two rows has the same values for the columns in this X, attributes in X. Okay, columns corresponding to attributes in X. So A1 and A1 here. So what we can do is you look at Y part. Y is E name. So look at Y part. Y part has A2, B22, B32. So here you have a symbol. So algorithm says if any of the rows has a symbol for the column, okay, then set the other rows to that same A symbol in the column. So what you can do here is you have one A symbol here. So you can copy that to A1 and A2. So corresponding to this A1, you override this as A2. Okay, B32 is overwritten as A2. Okay, that is solved. Again, you take the next dependency P number to P name, comma P location. So take P number B13, A3, A3. So two values are repeated, A3, A3. Okay, so corresponding to that, you have one A4 and A3. Okay, so here A4 is there, that is A symbol is there, so you can copy that to the other rows also. So A4, you get A4. Now take, this P number, P name, comma P location. So take two columns A4, A5. So here you get A4 and here you override this as A5. Okay, because if you have A symbol, then that will be copied to other rows. So A4, A5 and A4, A5. Then SSN comma P number to us. SSN comma P number. This is A1, B13, B21, A3, A1, A3. So all these are distinct. So no need to make any changes. So only thing, when you take P number, you take the combination P name comma P location. There you make change. And SSN comma P number. When you have a set of attributes here, you take that particular combo and check the values. Okay, corresponding to these two columns, the values should be equal. Okay, so here we have changed the values, and the last line says that if a row has only A symbols, then the decomposition preserves this non-additive join property. Okay, so here you have B's here in row corresponding to R1 and for R2 also, but for R3 you have all A's, which means that this decomposition preserves lossless or non-additive join property. Okay, now we'll have another testing, that is for binary decompositions for the non-additive join property. Okay, so you have binary decomposition, which means that your universal relation is split into two relations. Okay, so a decomposition D is equal to the set R1 comma R2 of capital R has the lossless non-additive join property with respect to a set of function dependencies F on R if and only if either this condition or this condition is true. So the function dependency R1 intersection R2 determines R1 minus R2 is in F plus, F closure, or R1 intersection R2 determines R2 minus R1 is in F closure. Okay, if these two conditions, any of these two conditions satisfy, then you can say that this particular decomposition has a lossless join property. You take R1 intersection R2 and R1 minus, compute R1 minus R2. So take one example. So teach, again teach, then you have these function dependencies FD1, that is student comma course to instructor, then FD2 is instructor to course. So you have two relations. This is binary decomposition R1 to R2. So take first binary decomposition. There you take R1 intersection R2 and that determines R1 minus R2 if that is in F closure. Okay. So here R1 intersection R2 is student. Okay. So student determines, suppose you have R1 minus R2. Okay. R1 minus R2 is instructor. Okay. Student determines instructor. That is not in F closure. Okay. Or you can even have R1 intersection R2 determines R2 minus R1. Okay. So student R1 intersection R2, you get again student and you take R2 minus R1. So you get course. Okay. There also student to course. No such functional dependency is there in F closure. So take the next decomposition. That is R1 is course comma instructor, R2 is course comma student. So here course, when you take R1 intersection R2, you get course to either student or either instructor. Okay, so if you perform R2 minus R1, you get student. When you perform R1 minus R2, you get instructor. So which means either course to instructor or course to student. So no such function dependency in F closure. And when you consider R1, R2, so you have R1 intersection R2, that is instructor to course or instructor to student. Okay. that instructor to course is there, but instructor to student is not there. So which means you cannot preserve this functional dependency. Okay. So it is not going to preserve this lossless non-additive join property. So that is for today.